I think a bit, but it's okay. It's okay.
Okay. Yeah, just shout out if you stop hearing me. Okay, let's see if we can bring that to a successful conclusion. All right, so last time, yesterday, I told you how to quantize free theory, which is not, that exciting, but today I'm going to finally say something about the interaction. However, in order to avoid subtle functional analytic issues, I'm going to restrict to the most boring observables ever, so the regular functionals. So restrict. So this is for the purpose of this lecture, not be, well, you can do better, but obviously that requires more work. So restrict to regular functionals. And I recall what it means. So it means all derivatives are smooth sections. Okay, and with that restriction, the free theory is the following. So to a region O, we associate the space of regular functionals on the cotangent bundle. So this is regular, the odd cotangent bundle functionals on the shifted cotangent bundle. This is the extended configuration space. Sorry. In case we want to add more variables, supported in the region O, and everything for the purpose of this section will be formal power series in H bar. And here we have a differential as 0, which is a bracket with the quadratic action. And we have the star product that I introduced yesterday. So that's the free theory. Now, for the purpose of interaction, I need to introduce one more product, commutative product for a change. So, but first, let me introduce something called time ordering operator. T is defined for F, well, let's say on this space of irregular functionals, formal power series by, so T is now an exponential kind of operator. So we have H bar over 2, and here we have a second derivative, d over d phi squared. This has some signs in it, which I'm not spelling out. So this should be with appropriate signs. And this is contracted with something called the Feynman propagator. So that is yet another integral kernel. So delta F is I12. We had those retarded and advanced green functions. So we have a sum of those plus the symmetric part that we used in the definition of the star product. So this is the Feynman propagator. And note that I'm doing things on general globally hyperbolic spacetimes. So if I was on Minkowski, this would be the Feynman propagator from your physics textbooks, if you have some on your shelf. And just a remark to connect to the Poisson bivector. So note, by the way, that pi was given as the difference of retarded and advanced green functions. So here we have a plus in the definition of delta f, and delta f is symmetric. So this is symmetric. Okay, and this will lead to a commutative product, which we call the time-ordered product. And let me define it here. The time-ordered product T is defined. So one way of writing it is just as a deformation of the pointwise product of functionals using that map T. So it's given by T minus 1 on F, pointwise product, T minus 1 on G. So in a sense, you can see, well, this is equivalent to the pointwise product that we had in the classical theory. So equivalent to the pointwise product of the classical theory. And that product can be graded. So I'm just using the dot notation, but this, if we are working on a graded manifold as we do, this product is also graded. But today I'm going to hide all that graded geometry stuff because it's not very relevant to the story. Just add some signs here and there. Okay, so what is that time-ordered product? And well, if you studied a bit of quantum theory or heard about it before, then you probably know about path integrals. So this time ordering operator I defined here is actually related to path integrals. So formally, is there a question? I have to check the chat a bit. Okay. So formally, T f of psi, this is formal, so I'm writing it in quotation marks, is the same as the convolution pi minus psi d mu with a measure, which is a Gaussian measure with covariance given by this Feynman propagator thing. Psi. So this guy here, again, formally is the oscillating Gaussian measure with covariance delta f. So this is a sort of a dictionary to path integral. So taking this T is the same morally as doing path integral. So this is path integral. So this whole approach of perturbative AQFT to interaction, to quantizing field theory is very much inspired by the path integral approach. So it shares the combinatoric of the path integral, although the formulation is different. So here you work with differential operators instead of working with those integrals, and that is actually well defined. So there is a big advantage of actually doing this. And another remark about the time-ordered product, why is it called time-ordered? Well, it is actually a time-ordered version of the star product. So here is another remark. So remark, T is the time-ordered version of star. This is still the product of the free theory. So we have that F time ordered G is the same as F star G if the support of G comes before, or maybe more precisely, not after F, okay? And it is G star F if the roles are reversed. So the support of G comes not before the support of F. So this is this important causality relation that relates these two products. Okay, so these are the basic properties. And what I'm going to use this for is to define interacting fields. So, sorry, interacting observables. So the first step is to define the formal S matrix. Is defined by the following. So S of lambda, now I take the time ordered version. Let's see. So that, no, actually I will use that convention. S of lambda V, this is the time ordered exponential of I over H bar, lambda, and now time ordered version of V. Let me now break this down for you a bit. So this lambda is now interpreted as the coupling constant. So V is the interaction we are introducing into the game. So lambda is coupling constant. And for now, this is going to be another formal parameter. So another formal parameter. And V then is the interaction. So interaction. So we are now interested in a theory which is given by the Lagrangian L0 plus V. So total Lagrangian L is L0 plus V. So yesterday I dropped that V from my consideration, so I just defined the free theory, but now I'm going to bring that V back. And here applying this T here can be seen as a choice of normal ordering. So this is something like normally ordered version, or just normally ordered V. Okay, so with all these caveats, this object here is now a formal power series in lambda, and because we have here negative powers of H bar as well, Laurent series in H bar. So formal power series, or actually maybe started the other way. So Laurent series in H bar with coefficients in formal power series in lambda. So that guy, very formal, is the formal S matrix. And well, the reason to use it is to define the interacting fields. So define, or actually I should say again, interacting observables. Interacting observables are defined as follows. So given F, which is now one of those regular objects, I define, or actually, let me just take one without any higher powers in H bar. So let's just take F in BV regular and define the interacting observable corresponding to that. So this is denoted by RV. RV of F is given as the inverse of this S matrix star with the S matrix times time ordered F. So that's the definition. And this map here is called the retarded, so hence R, Müller operator. So you can think of these Müller operators as maps from free theory to the interacting theory. So far, so good. The formula is a bit involved, so it's not necessarily obvious why such thing is done. So this formula is due to Bogolyubov, and it goes back a long way. So this is something that was known in physics for a while. Now, fun thing is that you can adapt it to this slightly more mathematical framework, and this should be attractive to people. You can use this map to further deform the free star product to get the interacting star product. So, we're in the business of deformation quantization. So in the end, we want the deformation of the interacting Poisson, algebra interacting Poisson structure. So now the prescription to do it is to go more indirectly. So construct the free theory first and then deform it using those maps RV. So now the interacting star product is defined by, so F, let me decorate it with V because it corresponds to the interaction V. F star G, well, there is an obvious way to do it. So we just deform our free star product with those maps. And there are some interesting properties here. So one, I should have said that this retarded Müller operator, if we started with F, which doesn't have any H bars slapped onto it, RV of F actually still turns out to be starting at order 0. So it's not entirely obvious because the S matrix is a Laurent series, so it could have negative orders in H bar. RV actually has only non-negative. So starts at order 0 in the H bar. And here there is another nice thing. So let me put back that formal parameter here. So I should always remember to put it. So in principle, this would be a formal power series in lambda as well, but it can be shown that that part can actually be resummed. So this is convergent, or rather can be resummed in lambda. And for that, I'm going to give you a reference. There is a paper of Eli Hawkins and myself So I'm going to give you a precise reference in the notes. So that's the interacting star product. And okay, well, from the point of view of just the formation quantization, we are done early. So what remains to show right now is how those structures play with the other guy here we started with, namely the differential. So I want to spend the rest of this talk explaining how everything that I introduced here right now relates to this differential. Okay, I think that's a reasonable point to pause for questions. So are there any questions?
Maybe one question. So far everything is local.
Yes. Well, no, sorry, not really. So these regular functionals are in general not local.
I mean local in the sense of assigned to some, what did you call it, causal set O.
Sorry, I didn't understand.
Whom?
Well, nothing at this point. Sorry, you're asking a question.
My question was, everything depends on this little causal neighborhood O that you defined in your first lecture, doesn't it?
Oh, in that sense, local. Yes, yes. Okay.
So will anything still be globalized, or will it just?
Oh yes, yes, yes. These things can be defined globally. So yeah, but they preserve that causal neighborhood. But they're well defined globally. So both the star product and the time ordered product. Also, the time ordering operator is genuinely local. So it also well, it preserves support, preserves that causal neighborhood, and it's actually a local operator.
Okay. Thanks.
In that sense, okay. This is an important point for what follows. In fact, that this one's local. Any more questions? Let's see. Oh, what is the meaning of this product physically speaking? If the question is about the time ordered product, then that's the path integral. So if you in physics you're interested in computing scattering amplitudes, cross sections, and so on, and that you do using path integral. So secretly you're actually computing time ordered products and expectation values of time ordered products. So if you want to compute stuff, then this is actually something you can do. So you can take your favorite observables, compute their time ordered products, and this would tell you something about scattering amplitudes for those observables. Anything else?
Yes, I would have a question. It seems to me that the interacting star product is equivalent to the non-interacting one.
Yeah.
Okay.
Well, it's equivalent to, well, yeah, it is equivalent by definition, right? Yes.
Just struck me as being a little bit odd, but maybe I'm misinterpreting it.
Well, it's not as odd in a sort of algebraic setting, because in AQFT, we're kind of used to the fact that the global algebra is not very interesting, and it might be the same for the free and interacting theory, but it's the local algebras which count. So it's really about the way you assign those algebras to regions, which is different for the free and interacting theory.
Okay.
But yeah, otherwise, I mean, there is a similar situation also for the classical theory. So in the classical story, there is also a classical Müller operator that intertwines the free and the interacting Poisson brackets. So the non-trivial information is really in the functor, you know, in the morphisms rather than in the objects.
Okay, thanks. That clarifies it.
Okay, so yeah, let me carry on then with the differential. So an obvious next question, which I want to ask, is okay, well, we had this differential graded algebra with a 0 and the product star. What about the product T? So we have a new product, we have the old differential. So yeah, so what happens? And interesting things happen. So note, I want to check if S0 happens to be a derivation with respect to this time-ordered product. And the answer is almost. So there is a bit which looks like a derivation. So yeah, there are some signs related to the grade of X. So this is graded Leibniz rule. So everything looks good, but there is an extra. So there is an extra term, which is a twisted version of the anti-bracket. Remember that we are working now here in the situation where everything is twisted with the time-ordered product. So here, this is defined as T minus 1 bracket Tx Ty. This is the anti-bracket. So S0 is a derivation with respect to the time-ordered product modulo the bracket. And this is a very nice structure. And I've heard many names of this structure in the book of Costello and William. They call it Bellinson-Drinfeld algebras, so BD algebras. So I'm going to carry on with that. So this gives us a structure of BD algebra. So the differential, the product, the bracket, they all can be then organized in the structure of a Bellinson-Drinfeld algebra. Another fun fact, this bracket is local. So if X and Y happen to be with disjoint support, then it vanishes. So we have sort of derivation property for things which are with disjoint support, which makes a lot of sense because we know that the star is a derivation. And if things are with disjoint support, then star and T are obviously related. So it's only at the overlapping supports that things can go wrong. And indeed, this is quantified by the bracket. So that's one observation. Another observation is that, okay, well, let's try to untwist everything. So we know that this time-ordered product is related to the pointwise product via this time ordering map T. So now let me untwist everything and untwist the product and twist the differential. So something always has to be twisted. So now define the new differential. I will call it S0 hat, which is T minus 1 composed S0 composed T. So this is the twisted version. And yeah, after some calculation, we find out that in order 0, it gives us S0 again. And it has a bit of a correction, which is of order h bar. So you can think of it as quantum correction times something, well, some operator that turns out to be the graded Laplacian on our odd cotangent bundle. So this quantum correction is called the Vivi Laplacian. And again, modulo signs, delta is d squared over d phi of x, d phi dagger of x. So this is a graded Laplacian which is a natural structure on this odd cotangent bundle that we are working on. So this is a nice thing geometrically. Another way of arriving at such conclusion would be to go via path integral, which works in finite dimensions, doesn't work in infinite dimensions. So in the path integral, you could relate the appearance of this Vivi Laplacian to things vanishing modulo total divergence. So there is a geometrical way of getting something like that, but here it just comes out of algebra, just comes out of these structures we introduced with the time-ordered product. Okay, so with that, I have now the following. So obviously this formula above now holds also if I untwist the product and twist the differential. So we have that this differential now acting on the usual graded product. So I can now repeat everything just with the usual product. And then here I have the honest anti-bracket. So this is the version where the differential is deformed and the product is undeformed. So there are two pictures, two ways of looking at things. One is with undeformed differential and deformed product, and the other is with the deformed differential and undeformed product. And this actually kind of historically, these were two ways of formulating path integral in algebraic way. So there was the pAQFT approach where we worked from the very beginning in terms of deforming the product, so constructing those time-ordered products. On the other hand, now recently, there was this approach of Costello-William, where the idea is to actually quantize the theory by deforming the differential. So this is this other picture, and these kind of came together. And we realized the obvious relation. So the obvious relation that we can now write is that this assignment here of structures on the pAQFT side, pAQFT, can be now related by the map T-1, which now becomes chain morphism to, again, Vivi reg of O. So the vector space here doesn't change, only the differential changes and the product changes. So this is Costello-William. Okay, but it's really well doing the same thing, but it's packaged differently. And more about the relation you can see in my paper with Owen and William, where we worked that out in a bit more detail. Okay, so finally, let me go back a bit here. So now I want to, so this story, sorry, I should say that. This story, I haven't used the interaction at all yet. So this differential I defined here as 0 hat can be thought as the free quantum BV differential. So I should call it properly. So this is the free quantum BV differential. Okay. And now, in order to incorporate interaction into the game, I'm going to come back to these two structures. So there is the formal S matrix, and there is this interacting star product. So there is a first natural consistency condition that I'm going to need, which is that this S matrix has to be invariant under the linearized BV operator. So condition on this whole construction to proceed, assume S of V to be invariant under S0. So how does it look like? So we have S0 on this time ordered exponential I t on V over H bar has to be 0. And again, we can do a bit more explicit computation. It's actually also useful maybe to rewrite that in terms of this quantum BV operator. So note that this is the same as S0 composed with T applied to the honest exponential IV over H bar. And now, well, if we compose with T minus 1, nothing really happens. To the right-hand side is also 0. So this condition can be also phrased as the quantum BV operator acting on the S matrix. Now, in terms of the pointwise product is 0. So this is just equivalent way of phrasing it. And we can find out what it is explicitly. Again, it's a computation. All these things are actually given very explicitly. So we find that this is IV over H bar. There could be some prefactors, which I don't remember. But what we get here is there will be a term with the free bit of the differential acting on the exponential. So that produces the bracket of, oops, that's the wrong way around, the bracket of V with L0. And there will be a term where this Vivi Laplacian acts, and that produces two terms. So one will be 1/2 of the bracket of V with itself, and another is just the Vivi Laplacian acting on V. Okay, and then we can also assume extra that this free theory satisfies the following equation. So with that assumption, we can rewrite this as 1/2. Oh, sorry, that shouldn't be S. I'm so sorry, I just use inconsistent letters. So that should be L. So with that assumption, we can rewrite the above condition as L0 plus V, L0 plus V minus IH bar delta S0 plus L0 plus V equals 0. So this is a condition, algebraic condition, that the Lagrangian, the full Lagrangian of the theory, right, has to satisfy. So this is phrased now in terms of the full Lagrangian, and there is a corresponding equation in terms of the free Lagrangian. So the free theory has to satisfy this kind of equation, and the full theory has to satisfy this kind of equation. And this equation has been known also for a while in physics and in mathematics, and it's called the quantum master equation. So this is the quantum master equation. And the way we arrived at this in the pAQFT framework is starting from the invariance of the S matrix. So this is something which was actually relatively new. So this was what we have shown in the paper with Frenhagen from, I guess, well, 2013, I guess. So yeah, this connection between the algebraic condition that was already known in the Vivi formalism and properties of the S matrix that is actually not that old. But it's a nice thing. Now, why do I need that? Well, first of all, I'm going to need that for the definition of the quantum interacting Vivi operator. Okay, so I have this S0 hat, but now I really want to have the interacting version of that. And again, you know, I have these maps RV that relate free and interacting theory. So why not use them? Okay, so next step, I define the interacting, so the full quantum BV operator in the interacting theory. Okay, so this is S hat, and it's defined as RV minus 1 composed with S0 composed with RV. So if you look back at the definition of RV for a second, so that's here. If you now were to put V equals 0, well, this term goes, and what we are left with is just the T operator. So for V equals 0, so 0 interaction, we are back to the free quantum BV operator. So this is the interacting sort. And now we can do a computation to find out what this is. And assuming quantum master equation, this turns out to be a local operator. So quantum master equation in this setting, in this formulation, guarantees that at the end of the day, we get a local operator, and not just local, but also very nice. So again, it's a computation, and we have one term, which is the bracket with the full action. So this is, in other words, just the classical Vivi operator. And we have this quantum correction given in terms of the Vivi Laplacian. And that's it, okay? So, and well, both the Vivi Laplacian and the bracket are local, so this is also local. So I defined the quantum BV operator. The nilpotency is clear by the definition. So the only thing that is not clear is the locality, which actually needs this quantum master equation. Okay, so just to summarize, why do I need those guys for? Well, it turns out that if I want to compute at the end of the day quantum observables, so recall that this BV operator in the classical theory, we used it to compute gauge invariant on-shell observables, right? So to find the physical content of the theory. Now here, if we want to compute the space of quantum observables, this is the guy we want to use. So this chain complex with the quantum Vivi operator computes the space of quantum observables of the theory. It's not a differential graded algebra anymore for the same reason I said before, that yeah, S fails to be a derivation with respect to the time-ordered product or with respect to the pointwise product in this formulation. But we still have a vector space, we still have a chain complex, we have a nilpotent operator, we can compute the cohomology. So yeah, so this is what this whole gadget is for. Okay, so that essentially finishes this story. So are there any questions at this point, or requests what I should explain more? Okay, so maybe let me finish a bit early, and if there are more questions, then I would be happy to answer. I didn't think there is much point in starting yet another topic at the moment. Okay.
Thanks a lot, Kasia.
Okay, so I see one nice question which prompts some longer discussion. So where are the infinities? This is a great question. So yeah, let me maybe talk a bit more about it then, since I have time. Where are the infinities? That's in the definition of the time-ordered product. So what I told you up to now is the time-ordered product for regular functionals. So regular functionals well, this is an easy observation. If we want them to be local, they can be at most linear, because quadratic things, if they are local, the derivative already gives a delta distribution. So regular functionals are non-local if non-linear. Okay, so the time-ordered product I defined gets singularities if I want to extend it to local arguments. So so this is an observation, and the problem, the renormalization problem, is how to extend T to local nonlinear functionals. Okay, and this is what in our framework is the renormalization problem. So this is the renormalization problem. And so how do we solve it? Well, there is one observation that is useful. So let me define Tn of F1 to Fn as the time-ordered product of these n arguments. And this is well defined for local Fi's as long as their supports are disjoint. So this is well defined for Fi in, say, Vivi log, as long as the supports are disjoint. Okay, so now we know that. So the problem of defining these time-ordered products for local functionals can be reduced to the question, how do we extend those guys to things with coinciding supports? So we want to extend this to functionals with coinciding supports. Okay, and in particular for the S matrix, you would have to evaluate these Tn's at the same n copies of the same functional. So obviously you need things to be well defined and coinciding supports. And this is where the Epstein-Glaser renormalization comes in. So this is Epstein-Glaser renormalization. So this can be understood as the quest to find this family of Tn's to, well, some larger space, which before I denoted the space of microcausal functionals. So we want to find that family of maps, and is a natural number, so that certain axioms, certain properties are fulfilled. And the important guiding property which allows us to actually construct those maps is the following. So there is something called causal factorization property. Okay, so this says if we have a bunch of functionals so that we can split their supports. So here we have the supports of, let's say, Fk plus 1, Fn. So these come earlier than the supports of the first bunch. Fk, oh, sorry, this should be k plus 1, k plus 2. Yeah, so then this guy factorizes. Oh, sorry, just, yeah, let me mute myself quickly. Okay, I'm back. Okay, so just finished writing the causal factorization property. So with this property and some further requirements, one can construct this family of maps. And at each step, sort of the functional analytic question is to extend certain distributions which are defined everywhere outside the diagonal to the diagonal. So it's an extension problem for distributions. And this is where infinities come in, okay? So instead of trying to multiply infinities together and do things that are not very well defined, we have we phrase this as a problem. Okay, we have some singular objects that are defined outside those dangerous points. How do we extend these to distributions that are defined at these points? And due to this, nice framework of Epstein-Glaser with some theorems of microlocal analysis, you can show the existence of such extensions, and then the ambiguity, the freedom you have, is related to the renormalization freedom. So there's this whole renormalization procedure that can be phrased in that language. Sorry, that was a very long answer to this question, but the question deserved a longer answer.
Okay, are there more questions?
I just have a very silly question. Thank you very much for your talk, your lectures. It was very nice.
Yeah.
I guess behind this, is there like a signal model behind them?
Oh, well, that's a very good question. I don't know, maybe. So okay. So this interacting star product, where is it? Now define this interacting star product. Yes. Okay. So in this paper with Eli Hawkins, we found this nice non-perturbative in lambda formula, a combinatorial formula for that product, which involves Feynman diagrams, but these are not the same as Kontsevich diagrams. And we have indeed shown that our construction, our formula differs from the one of Kontsevich, which is good, because in infinite dimensions, we know that the formula for Kontsevich doesn't work. So that wouldn't be well defined. This is well defined, so it has to be somewhat different. But yeah, we would be really interested to see how that story possibly relates to Poisson sigma models. But that's an open question.
Thank you.
Are there more questions? It doesn't seem the case, so I suggest we also thank Kasia for the very nice mini course this week.
Thank you. So this is the last lecture. There are still exercises to come, but since this is the last lecture, I thought it would be appropriate to thank the organizers of this really nice event for all your efforts and making this happen and making this work despite all the obvious difficulties. So thank you very much. This was really wonderful. I still want to come to Freiburg, but at a later date.
That's right.